Okay, we're at lecture 8 in the series on special relativity, electrodynamics, and general relativity. And this lecture will consist of two parts. Our aim is to understand Maxwell's equations and the wave equation of electrodynamics. And the crucial element in this discussion is to write Gauss's law as a covariant equation and then boost it and see and check that it's a covariant equation and get a few surprises along the way. Okay, so we'll start with Coulomb's law, okay, that everyone's familiar with. You have a charge Q1 at the origin. It's fixed in a particular frame, in this case frame S. And then you measure the force of another charged particle, the distance r away. And you find a force that falls off as the square of the distance between the source and the sink. Okay, and is along the line of sight between the two. And it's then convenient when thinking about the force between the two particles to write the force as the charge of the sink, of the particle that's moving about, okay, times the electric field generated by the charge that's at rest at the origin, and I write that as E vector of R vector. Okay, we're all familiar with that, and that's experimentally verified, and it's true as long as the charge sits at the origin and you've waited a long enough time for everything to be stationary, static. Okay, we want to ask a question: is this law fundamental? Well, it's certainly okay as long as there's nothing else in the entire universe except that source. Okay, and then I can calculate the force on the sink, Q2. However, let's just say you move into somewhere into the space a conducting plate. That's a plate at a fixed potential, as you know from your earlier courses. And so in that case, the electric field has to be perpendicular to that plate. So I bring a plate in from far away, and it's going to distort the electric field, okay, over the whole space. So we see that that Coulomb's law in this case is a very special, particular solution to a more general problem, and we want to find out what that general problem is. What's the general physics behind Coulomb's law? Coulomb's law depends on boundary conditions, a static charge, things that we have to generalize. We have to get around them. We have to think about more general situations, and we're going to be pushed in that direction, okay, to write down local differential equations instead of a solution of a problem. We want to see how the problem is formulated. At this point, we're not so keen on seeing how it's solved. So a different attitude. So we need a local differential equation to capture the idea behind Coulomb's law, and so we can apply it to all situations. Well, Gauss looked at this problem, okay, and he did many things. One of them was that he noticed that the presence of the charge at a particular position can be confirmed by measuring the electric flux emanating from it. Okay, so he said, I don't have to go in this case to the origin and see that there's a charge Q1 there. I can instead calculate the electric flux through any surface that surrounds that charge and infer the presence of the charge. So what did he have? What did he have in mind? First, he defines the electric flux as the surface integral of the electric field going through the surface of the integrand E dot dA. Now dA is the area patch anywhere on the surface. See here I have a sphere and I show an area patch dA. So it's a little bit of area, and it's a vector area. In this particular case, it points outward. Okay, so it's a unit vector that points outward, and the magnitude is just the little area of that patch. Okay, And so Gauss said if you do this integral over the surface, you'll get a simple result. Okay. In particular, I know what the electric field is here. I just plug that in. Okay. I do that here, and then I'll calculate my my integral by noticing that the patch has an area which is just r squared times the solid angle of the little area as perceived from the origin. Okay, over here. So I write that as d omega. Okay, I don't need to write that in any particular coordinate system, as we'll see, because it's a very simple problem. Okay, but I could write down the patch area in some particular coordinate system to do the integral in a general case. But in this case, it's not so hard. You see, the little patch, the area of that little patch, rises as r squared, the distance you are from the origin, because I'm doing this integral over a sphere that's centered at the source, Q1, and the sphere's radius is capital R. So dA of magnitude is r squared d omega. That's the area of that little patch. But now you see the integral is particularly easy. The r squared, the rate at which the area of the patch grows, is canceled by the rate at which the electric field falls, 1 upon r squared. So the r squared goes away, and I just have a free integral over the solid angle subtended from the origin of the sphere. Well, the solid angle in that case is just easily integrated, it's just 4 pi. Okay. So the right-hand side is just 4 pi k. K is the constant in Coulomb's law, times Q1, and that's the point. It's proportional to the charge. And how did I measure that charge at the origin? By looking at the total flux that emanates from that charge at any distance away from it. I mean, capital R canceled out. Okay. So that's curious, but let's make something more of it by again using more of Gauss's great insight into geometry and physics. He noticed that this result, that the flux of the electric field emanating from that charge is true for any closed surface around Q1. So that's a topic you've studied in your vector calculus, and you've derived Gauss's theorem. Okay, that's where it stays. In Gauss's theorem, remember, it tells you that the surface integral. So in Gauss's theorem, let's begin in the general case. We have a vector field, okay, defined in a Euclidean space, and we have some closed surface of any shape. And Gauss's theorem says that you can calculate on the one hand the flux of V through that closed surface. So that's just V dot dA integrated over the surface. And Gauss's theorem claims that that's the same result as doing an integral over the volume inside the surface of the divergence of the vector field. Okay, so it's divergence of V integrated over the entire volume. And I write that, you might write that as dx dy dz, or dr vector, or d3r, whatever notation you like. And here I've written it down here. Okay, and so that's Gauss's theorem, and that's a mathematics theorem. And the claim and the point is of the theorem is that this holds for any closed volume V, let it be smooth enough, with a surface S. Okay. So that means I can come back to this discussion of Gauss's law, the application to the electric field case, and simplify the right-hand side, because here on the one side of the equation I have the surface integral of the electric field, so I can write that as the volume integral of the divergence of the electric field, and that's what I do. Okay, and so that's what I do. So then I have that the integral over the volume, okay, any volume that encloses the origin is equal to 4 pi k times Q1, the charge inside. Okay, now the charge inside might be a point particle, or it might be distributed. Okay, so there might be a charge density underlying it, and the charge Q1 is just the volume integral of the charge density. We'll write it down for that particular case because that's useful for applications. Remember, all of the ideas we're presenting here satisfy the linear superposition principle. And so if I do any of these problems for point charge, I can take a whole bunch of them and get the same result. I will discuss it in just a moment in more detail. But remember, the linear superposition principle, you've met it before, and you know how handy it is. But in any case, Q1 might be the total charge of a distributed charge. So you might have a function rho of r, which tells you the charge per unit volume in that distribution. Okay, so when I see the Q1 here, I can write it therefore as the integral over a charge density rho. Okay, so now I've discussed Gauss's law and Gauss's theorem, and now I'll combine them. I'll see way over here on the left, there's a volume integral of the divergence of E. Way over here on the right, there's a volume integral of the charge density. Okay, and this equation has to be true for any volume, right? That's the power of Gauss's theorem. Okay, if it's going to be true for any volume at all, I can take them small, distort them, I can pinpoint the origin. It has to be true point by point. And so the divergence of the electric field is 4 pi k times the charge density. I'll usually, we always have that 4 pi k in there, but when I speak, I'll just say that, the charge density makes an electric field, and by that I mean rho is proportional to the divergence of the electric field. Okay, so let's take a look at this. Now we've inferred a differential equation for the electric field that holds everywhere. Okay, that's what we've inferred. Well, that's much more useful, of course, than Coulomb's law, because this is a statement about what happens at a single point in space-time. Okay, that the charge density generates the electric field. I don't have to think about what's happening far away or anything like that. This is just a local differential equation. If you give me a problem to calculate the electric field, you'll say it satisfies Gauss's law, that's this, with certain boundary conditions. And they'll affect the long distance behavior of the electric field, okay? But the local differential equation underlying all of this is always the same. So this is the fundamental state that underlies Coulomb's law, and that's what we wanted. It satisfies a linear superposition principle. It's a linear equation. By that I mean that if you solve on the one hand a problem with a charge density rho 1, you can calculate the electric field. And you can integrate it up and get E1 all over all space. You might have, on the other hand, another problem with a charge density rho 2. That'll give rise to an electric field E2. Now you can take the sum of these two equations, okay, and see that the charge densities rho 1 plus rho 2 in a problem where you combine the two charge densities, brought a charge in from infinity, say, near to rho 1. And that combined charge density produces the electric fields of the first two problems, right? So you might be able to use this fact to make a complicated charge density, rho 1 plus rho 2 plus rho 3 plus rho 4, etc. And you'll solve that problem by doing a bunch of very simple problems where you do rho 1 is proportional to divergence of E1, okay, and let's put them all together. Okay, so I can do that. Okay, but now I want to take this hint that this law is fundamental and write it in a way which is appropriate for special relativity. Okay? So here's Gauss's law. I've written it down just for a static situation. However, I might, for example, boost the charge to a velocity v in the lab frame. Okay, and in that frame, of course, I expect, okay, the Gauss's law will still be true. Okay, and at any point in that frame in which the charge density is moving, I can look at a point, okay, of position and time, and at that position and time, I can ask if there's an electric field there. Okay, well, certainly the charge density at that point, at that time, will generate an electric field, and I'm only interested in the electric field at that point. Okay. So all of the complications, perhaps, of solving a long distance problem or a problem with propagation or something like that disappears from this consideration. I'm just interested in writing down a differential equation for the electric field, and I learned from Gauss's law that the divergence of the electric field is equal to the charge density. I've seen it in a specific case. If that's going to be a general law, then I can boost the charge density and should work in the frame in which the charge density is moving. In which case I just look at that charge density in the frame in which it's moving, and I expect the electric field at any one of those points to be given by the charge density there. So I might have a very complicated problem, for example, of a charge density varying over space and time and moving with respect to me. Okay. Now I might want to think about the differential equation at some specific point in space. So what I could do, for example, then, is to boost to a frame, okay, in which the charge density at the point of interest r is at rest at a particular time t. I go to the instantaneous rest frame of that little bit of the charge density which is moving along. Okay. Well, as soon as I get to that instantaneous rest frame, then I know, just on the basis of a discussion of Coulomb's law, that the charge density, which is instantaneously at rest, generates an electric field at that point which satisfies Gauss's law. Okay. Okay, and then I can go back into the original reference frame. And it must be, okay, that then the divergence of the electric field at that space-time point, r and t, is proportional to the charge density at that particular point, r and t. Okay, it's very simple because it's a local, a local expression. There's no complication in thinking about propagation or anything like that. I could ask more difficult questions, perhaps. Perhaps I have a charge density moving along here, and I measure the electric field outside, away from that charge density. In other words, I try to solve the differential equation and get the long distance behavior like we did for Coulomb's law. Well, that's much more complicated, right? Because the electric field here will be determined by the charge density, but that information of where the charge density is at a particular moment, that information takes time to get to the position of the electric field. That time is the distance divided by r, and so I see the electric field at one point will be determined by the charge density at an earlier time, a retarded time. Well, that's complicated stuff, and do you think the electric field here is determined just by knowing the charge density? Well, it's not so clear. It's not so clear. Maybe the charge currents contribute as well. Okay, maybe some other aspect of the charge distribution does. It's not clear. I can't jump to a conclusion there. Okay, that's too hard for me. However, if I bring the point where I look at the electric field to the point where I'm looking at the charge density, then I get simplicity. Okay, okay, they're the same point. The only covariant expression that makes any sense is that the charge density at that space-time point is proportional to the divergence of the electric field at that same point. That's the only conceivable generalization of Gauss's law from the static situation. And we've argued also with imagining a boost to the instantaneous rest frame of the charge, okay, that really all I need to know is a static situation. I can make the dynamic situation out of it by doing various boosts and perhaps using linear superposition to generate a general charge density. Okay. So I make a bit of a creative step here and say I'm looking for covariant equations that can be true in all of Minkowski space or in all of space-time. Okay. Local differential equations look like the way to go, okay, because of their simplicity, that I'm going to measure the electric field right at the point where the charge is. Okay. So there's no so locality and causality go right in hand, and I can write that down and have both of those fundamental principles in the equation. And so that's what I've written down here. So for a general charge density, which is a function of R and T, I expect that the electric flux at that point to be given by Gauss's law as written there, with full time dependence, with full generality as to what the charge density is. That should be true in all of Minkowski space, point by point, right? Right? It's point by point. I don't need to know what the charge density is a little bit earlier. I don't need to know where the charge density is a little bit to the right. I can write down the differential equation for the electric field at that particular point, and that's all that I need to know. Okay. And that's a simple and fundamental equation, and that's going to be the basis for our understanding of all of the Maxwell's equations. Okay. So, well, we've studied the electric field. We understand how it works. We don't know very much about charge densities yet, so let's develop charge densities a little bit. Okay. The basic idea in the charge density is that a charge density is moving, it generates a current. Okay, we have a charge density rho in a particular frame. Then if that bit is moving with a collective velocity v, then we know we have a current density, which is just charge density times velocity. And you've used that in your more elementary physics problems to talk about currents through wires and things like that, right? If you integrate the current density across the wire, you get the total charge per unit time passing a point in the wire. And so you've seen this before. And so that's the basis. I want to understand rho and j. I want to understand them together. They're aspects of the same thing. Okay? So I want to understand how they behave under boosts. Okay? That's one of the things I want to understand. And then the second thing I'll want to understand is current conservation. Okay? Charges don't pop out of thin air, or if they do so in a way that conserves a charge. So we want to talk about the conservation of charge in a way that's compatible with the principles of relativity. It better be a conservation law that's local and causal, because we know from our experiences with Newton's third law that non-local conservation laws are not covariant. You boost to another frame and you lose the conservation. Okay. So let's take a look at rho and j, and we'll consider charge density of charges at rest. Okay, rho naught. It's like when I was just considering energy and momentum. I began with going to the rest frame of the particle. There it has a rest mass. I might call it m0. I usually drop the 0. And then I boost the particle and understand energy and momentum. I'm going to do the same game here. So I go to the rest frame of a charge density, and I call that density rho naught. Now I want to boost it to another frame, okay, to see what current is generated. So I make a boost to a velocity u. We're going to generate a current density, which is given by the charge density times the velocity. First thing to ask is, how is rho related to rho naught? Okay, for the moving charge, the current density will be proportional to the charge density. That's rho for a moving charge. How is that related to the charge density in the rest frame of my charges? Well, what is it? Well, the charge density is charge per volume. So I consider a little volume V. There's a certain charge in it, okay, and that's what it'll be. Now I can look at both numerator and denominator and simplify them. The charge in a volume, well, charge, of course, that's the total charge. That charge is, of course, boost invariant. Right? We've discussed that before. It's an experimental fact that charges are scalars under Lorentz transformations under boosts. And what about volumes? Oh, well, volumes are not. If you take a volume and you boost it, then one of its dimensions will contract. And so under a boost, okay, V goes to V naught divided by gamma. That's just Lorentz contraction. So I see therefore that rho is related to Q naught over V naught, that's rho naught, by a factor of gamma. Okay, and just Lorentz contraction. And so therefore J, the current density, is related to rho naught by a factor of gamma, as written there. So this sort of looks familiar to me. Let's go back and compare these formulas to the formulas for the force momentum. Okay, remember the zeroth component of the force momentum is relativistic energy over speed limit, and the other components of the force momentum are just the good old momentum. In relativity, the energy, the zeroth component of the momentum is gamma mc squared, and the momentum in relativity is gamma mv, where m is the rest mass of the particle. Well, I see that the factors of gamma are the same here as they are in the 4-vector rho j, the collection of 4 quantities, charge density and current density. Okay, and that's what's stated here. So J mu, there's a 4-vector charge density, okay, or current density. It consists of a time component, which is the charge density, and spatial components, which are the ordinary current densities. I write them out like that. I write out what I've learned to write them out in terms of gamma, and I see that has exactly the same structure as the energy momentum 4-vector. So I learned that J mu is a 4-vector. So I know therefore how to transform my current density from one frame to the other. It's a 4-vector. It'll transform just like x mu, space-time, or like energy momentum. Okay, and so I've written that down. Here's how to transform the charge density and the current density from one frame to the other. I don't have to do any more work with it. Okay, I see it has the same structure as energy momentum, so it transforms like this, and that's very interesting. Okay, I see that when I transform from one frame to another, the components of the charge current, okay, the current density are going to mix with the charge density in the same way that space and time mix together. And so I've written down those equations here. Okay, and in your homework sets and in the textbook, you'll take specific examples of this transformation law and see that in some cases it just reproduces things that you already know, and in other cases it brings in a mixing of the quantities, which is new information for you. Okay. Okay. So that's critical to understand that. The next property I want to bring in is just current conservation. Okay, just the fact that charges don't pop up in any particular peculiar way in space-time, but rather the charge current is conserved. So I might look at it this way. Okay, I might look at a certain volume okay, in space-time. Here it's at rest in the lab. It's a volume with a nice closed surface S, okay, and it's nice orientable object, and I can write its patch areas, okay, on that surface, and then I can make its statement of current conservation. Current conservation will be that the charge per unit time that leaves the volume will leave it through the surface, okay, and if I calculate the flux of the current going through the surface, okay, then I can equate that to the time rate of change of the total charge inside the surface. So the charge doesn't just come or go, it simply flows continuously. Okay, that's a statement of conservation. So if the amount of charge in a certain volume goes down, then I know that charge currents are flowing out. Okay, and the statement of that equality is written down here as an integral. Okay, the flux through the surface is equal to the time rate of change of the total charge inside the volume. Okay, but what, again, that's great, but what I really want to do is to write it as a local conservation law. Gauss to the rescue. Okay, here I see the flux of J, but by Gauss's theorem I can calculate the flux of J by integrating over the volume of the divergence of J. So that's the next step that we do. Okay. So I learn, okay, that the integral over the volume of the divergence of J is equal to the time rate of change of the charge inside the volume. Okay, but that has to hold for all volumes, that idea. Okay, I didn't have to specify anything particular about those volumes. I can distort them and make them with surface areas that are rather peculiar. It has to be true for all volumes, so it must be true point by point as equality of the integrands here. And so I learned that the divergence of J plus the partial derivative of the charge density with respect to time is equal to 0. Right, I'm looking at a particular point, so I differentiate with respect to t as a partial derivative because I'm looking at a particular point in space and seeing what's happening right there. Okay, so that's going to be my conservation law. Okay, now we should check that this is a local covariant conservation law. Well, let's just look at the derivatives here. I see a gradient and I see a time derivative. Okay, well I've met that before. I met the 4-vector d sub mu as this derivative with respect to x mu. It's this collection of d by dt's and d by dx's, or d by dt in gradient. And I know that's a 4-vector. Okay, we proved that. It was just an application of Lorentz transformations, okay, to the case of differentiation with respect to space-time. We used the chain rule, okay, and review that in the textbook if there's any concern there, okay. So now this is a 4-vector. I know that the current J mu is a 4-vector, so I take the dot product of them. That's an invariant under boosts. I can write it out, and I do so. I write it out here, and I see that that's just the left-hand side of my conservation law, so that's equal to 0. There's a Lorentz invariant statement because it's a dot product of 2 4-vectors, so it holds in every frame if it holds in any one frame. Okay. Okay, so that's critical. Okay, so now we have Gauss's law as I hope a covariant local differential equation in Minkowski space. We're going to investigate it a bit. That's why I'm a little bit hesitant about it. We're going to prove those things. Okay, and we have on the other hand the conservation of the charge current, and it's expressed as a local differential equation. So this conservation law has no difficulty with being boost invariant, as we see right here, because it expresses the fact that at one particular point in space-time, the total charge at that point can change with time, but it does so by generating a flux either in or out of that particular point. That's what this equation means. The time rate of change of rho at a point is equal to minus the divergence of j at that point. Okay, so it's a local equation, and it can be and it is covariant as we've seen. So we'll come back to part 2 of this lecture, and we'll find Maxwell's equations next time.